Thanks very much for the invitation and for the introduction. It's a great pleasure to visit Kyoto for the third time. So yesterday when I arrived, we had to do some administrative things, and I was given a certificate that officially appoint me as a visiting professor under a certain program that supported the visit. So I asked Atsushi, what is the purpose of this program? And he said the purpose of this program is for globalization of Japanese universities. So I hope that you find the subject of this series of lectures relevant, because we will be doing quite a lot of globalization. Okay, because I guess there seems to be quite a mixed audience here with experts and maybe some students. So at the beginning, I think I will err on the side of being on the slow side, I guess. So I may be going slower than what some of the experts might prefer. So okay, so as Atsushi mentioned, the subject is, that I'll talk about is on globalizing supercuspidal representations. And I'll define some of these terms as we go along. And even though the focus is on a function field, which is a characteristic p bigger than 0, but in fact many of the things that I say will work for even for number fields, which are characteristic 0. Okay? So at the beginning, let me start with K, a global field. So K is either a number field, for example, like Q, or it could be a function field, like, for example, Fp brackets T. Okay. So of course, by a function field, we mean the function field of an absolutely irreducible smooth projective curve over a finite field. So, for example, okay. As usual, let A be the Adele ring of K. Okay. And so let me take H, a connected reductive group, defined over K. So for example, for the sake of concreteness, you can take H to be GLN. So in general, such a group is will be a closed subgroup of some GLN for appropriate N. Let Z be the, so how do I write this? I write, it's the center of H, but which may be disconnected, so I take the identity component. So this thing is a torus, a central torus in H. Okay, so that's the basic setup. Then I want to define, introduce the notion of automorphic forms. So what is an automorphic form? It is, so I want to give a precise definition, but simply I'll say that it's a function f from, okay, maybe even before I say that, let me say that having introduced this, so I can take points. So, for example, since the Adel ring is a K algebra, I can take the adelic points of my group H. Okay? So I get a locally compact group, and it will contain the set of K rational points. And in fact, this is kind of a closed subgroup. Okay? So this is a discrete subgroup. So very much like, so it's similar to R containing Z, right? Okay. And so I guess I have to postpone this a bit. And if you take the quotient, so if you can take H. Okay. Well, if you are in the R containing Z situation, R mod Z is compact, right? So here is it's almost compact. It's not exactly, but if you mod away also this central part, then this thing, well, it's still not compact, but at least it's of it's a finite volume. Okay, so that's basic setup. If you have any questions, just stop me and ask. Okay. All right. So now let me remind you of the notion of automorphic forms. So what it is, an automorphic form is simply a function on this coset space. Right? Well, taking complex value. Okay. Now, so of course there are some conditions that it satisfies. Let me not spell it out. Satisfying. So the conditions would be some smoothness. You want your function to be continuous. In fact, more than continuous, but this is type of a continuity assumption. Smoothness, finiteness, okay, and growth, conditions. So, for example, you don't want sort of exponentially increasing function. You just want functions of polynomial growth. Okay, so in any case, I will let AH be the set of such automorphic forms. Okay, so it's a space of automorphic forms on H. Okay, now we have this center, so sometimes we may want to fix the central character. So I will maybe just write this. So this will be those F in AH such that maybe I write something like that. Or H in HA and Z in ZA. Okay, so I'm basically fixing a central character. So this here is omega is one-dimensional character of Z. Okay, and the point of this space is that it has an action of HA by HAX by right translation. So the right translation action would not destroy the left invariance under HK, right? Because the left and right, they don't see each other. So. Okay, so that's the object. Now, on the other hand, we have the notion of L2 functions. Okay, so this is another, maybe another functions. Okay, so this is just functions which are functions which are like that, and maybe with this central character condition. Okay, so let me just copy it. So okay, so here maybe instead of taking this in a C cross, let me take it to be a, you can take it to be a unitary character. For example, this is the unit circle in a C cross. Okay, so if you have a function with this property, then when you take the absolute value of this function, it will be a function on H A mod HK mod ZA, right? Because this has absolute value 1, so it ties. And then it makes sense to require that I'm going to denote this like that. It will be finite. Okay, so these are L2 functions on this space. And we'll denote by something like that. The space of such L2 functions. Okay, and this space, again, you have an action of HA also by right translation. Anyhow, you have two spaces of functions which may have nothing to do with each other. I mean, they are different conditions. Right? These are L2 condition, this is some smoothness and finiteness conditions which I have not specified. Okay? But they are not so, it's not as if they have nothing to do with each other. So if you try to take the intersection, okay, you see that there will be quite a number of things in there. Okay, it will be quite big in some sense. And okay, so maybe I call this. I would denote it like that. Now, inside here, there's a certain subspace called the space of Cup's forms. I mean, it's somehow it's not the whole thing, but it is somehow the most important part. Okay, so so what is a Cup's form? So here. So definition. I guess you don't even say this. So if you have an automorphic form, you say F is a Cup's form if the following conditions hold. So for all parabolic subgroup P. So parabolic subgroup would be, for example, you know, those block upper triangular matrices in GLN. That's the Levy decomposition of H. Okay. Maybe I should say a K subgroup. Okay, subgroup defined over K. Then you want this this integral to be equals to 0 for all H. Okay, so recall my notation that this thing means nk mod n. Okay, and anyhow, this you can think of this as a function of H. Okay, and this function is called the constant term. Constant term of f along n. Okay, so a Cup's form is an automorphic form such that the constant terms along all possible n equal to 0. So this is, I guess, you know, motivated by the usual notion of modular forms. You have modular form, you have Fourier expansion, and you say something is a Cup's form if the constant term of that Fourier expansion is 0. Okay, so that defines this space of cups forms. And okay, so one property of this space is because it is it's a subspace of L2, right? So you can take the closure. Okay, so you can set L2 cups H to be the L2 closure of this thing. This may not be a closed subspace. And one property is that as H module, okay, so this space, by the way, is closed under right translation by H. Again, because the condition to be satisfied is specified on the left, right? So if you right translate this function f by something on the right, it doesn't interfere with this condition. So this is a HA module, and in fact, it is a semi-simple HA module. In other words, it will decompose into a direct sum of irreducibles. So any irreducible summand, any irreducible constituent in here will be called is called a cuspidal representation. Okay, so that defines what I mean by cuspidal representation. And in fact, one might say that the so-called global Langlands program the goal of it is maybe one aspect of it is to understand this HA module. Understand is a very imprecise word, but understand the HA module. Okay, so more precisely, what does understanding mean? It means, for example, you want to classify the irreducible summands, right? What are all the irreducible cuspidal representations? Or what are you going to classify it by? So more precisely, you want to classify these so-called cuspidal representations in terms of so-called Galois representations, okay, maybe plus some extra data. Okay, and we'll come to this later on. So today what I want to discuss is, well, we have defined a space of cups forms. We say that it is a main object of interest in the global Langlands program, but a priori, just from this definition, right, it's not clear that such a function exists. I mean, of course, the zero function is satisfied this, but it's not a priori clear that there are non-zero cups forms. Okay, so the goal maybe today I want to just talk about how to construct some examples of cups forms. Okay, so the question I want to discuss is how to produce non-zero cups forms. And of course, there could be many ways, okay, a priori, but the particular method, I'm going to discuss a particular method called by the name of Poincare series. And actually, this is a very simple-minded method. I mean, because what it is basically you are averaging over a group. That's what this Poincare series is about. Okay, so of course you want to construct something, you have to start with some ingredients. I mean, you cannot produce something out of nothing, right? So what is the initial ingredient that goes into this method whose output is going to be, an automorphic form? Well, okay, so you start with, hopefully a non-zero function. Let's say a compactly supported smooth functions on HA. Okay, so maybe I say what this is. I mean, so you see this space is going to be a restricted tensor product as so here V runs over all primes of my global field. Okay, so all places primes of K. Okay. So for example, if K were just the rational number Q, then this will be all the usual prime numbers together with an Archimedean prime, okay, for the usual absolute value. But if K were the function field of a curve Y over a finite field, then what are these places? These places are, if you wish, depends on how you want to think of your curve. You will say that it's a close point of my curve, if you think of the curve as a one-dimension scheme. Or you might say, if you think of your curve as, if you identify the curve with its k-bar points, let's say, k-bar being the algebraic closure, okay, then you would take the places to be Galois k-bar over k orbits on this set of points. Okay. In any case, okay, so it is, in other words, these functions are very, so the point of writing this equality is to show that whatever these functions are, they are functions on some adelic group, but in fact they are built up from functions on this local group, so to speak. Okay? Because all you have to do is you take, for every V, you take a function on this local group. Right? So this local group is either a real Lie group or a p-adic type Lie group. And then you take a tensor of these, okay, functions. And that will produce a function. So anyhow, I want to say this ingredient is of local nature. Okay? And what is this prime? This prime refers to the fact that, so your F might be, a tensor like that, okay? Where FV will live inside the V part of this restricted tensor product. But the prime here refers to the fact that for all but finitely many V's, FV is not any, you can't choose this FV randomly for every V. Okay? So, such that for almost all V, FV is the characteristic function of, of some compact group, a maximal compact sub. Okay, so in any case, that is the ingredient for building this Poincare series. The point is whether it is of local nature. You pick FV, for every V you pick a function, you pick a tensor product, you get something like that. And since it's not zero, let's assume it doesn't vanish at 1, for example. Okay, now starting from this, you want to build an automorphic form, right? Which means, according to definition, you want to build a function on HA mod HK. Okay, well, this function is already a function on HA, so that's not bad, okay? But you would like it to be left invariant under HK, right? Okay, it's not, but you force it to be by averaging over HK. Okay, so you define, you sum over HK, F, because you want a function to be left invariant under HK, so you just force it to be, okay? Now, of course, whenever so it's clear that, if this converges, then it is a function on HA mod HK. Now, but what about convergence? Well, because this is an infinite sum, so you have to address the question of convergence. Well, in fact, the question of convergence is not so difficult. The reason is because when you sum over, so if you fix h, you know, you have to sum over this gamma. You only need to sum over gamma, or well, they have to be in hk, but also they have to be in the support of f times h inverse. But the point is that, you know, this intersection is happening inside HA, right? I mean, these are two subsets of HA. Well, however, this set is discrete. We already mentioned that it's a discrete subset of HA. On the other hand, this set is compact. Okay, because maybe I neglect to say that this sub C, this little c here, stands for compactly supported functions. So the support, whatever it is some compact subset of HA, even after you translate it. Okay? So now you have a discrete and a compact intersecting. So whatever it is, this intersection is both discrete and compact, so it is finite. Okay? So the point is that this intersection is finite. Okay, so this means that for any given h, this infinite sum is actually just a finite sum because only finitely many terms could be non-zero. So there's in fact no issue of convergence for any given h. Okay? And if you just move h a little bit, you can sum over the same finite set. Okay, so you have smoothness if you wish. All right, so we have a well-defined function at least. Okay, so the upshot of this is there's no convergence issues. Okay, and so PF, P for Poincare, is a well-defined function. Okay, now of course you ask, but you see there's no reason why it is non-zero. So you may ask, what about non-vanishing? Is this a non-zero function? Well, if you just want to produce some examples of non-zero function, you can, just because you can take this f. If you, for example, if you take f to be just a non-negative real value, right? So you can take f to be characteristic function of some compact set, okay? Or compact group in HA. Then each time you are summing up either 1 or 0, and so if you take your function to be non-vanishing at 1, for example, the identity element, then PF, okay, so if f is a function, like that, then say f1 not 0, then obviously PF of 1 is not 0. So it's not so hard to make it non-zero, okay? But suppose you take a f which is a genuinely C value, right? Then it's not clear because you might have cancellations as you sum up these things. Okay. Now, and sometimes you don't really want to put this because see the reason is because your goal in the end is not just to produce some. I mean, if your goal is to produce non-zero element in this space of automorphic forms, okay, then maybe we have it, okay. But if your goal is to understand the irreducible constituents of this space of cusp forms, okay, then you would like to know. So now, let's say you have a non-zero function. You look at the HA submodule generated by this function, and you want to know how that decomposes. Okay. Now, obviously, you would be good to produce something like that, such that a functions which generate an irreducible HA submodule. Okay, but at the moment, there's no representation theoretic contents, you see, so it's just producing functions. Okay. Now, but I want to discuss somehow maybe a less trivial way of showing non-vanishing. Which will be which we will use in a moment. Okay, and another question which we haven't discussed is, okay, so even if this were non-zero, why is it cuspidal? I mean, cuspidality has a condition of constant term, vanishing constant term, which we haven't checked. Okay, so these are there's still some questions. Okay, so I want to here another way of checking this non-vanishing as follows. Okay, so let's take this F as before, and suppose you pick a place V0 okay, of K. Okay, you pick and fix it. Okay, then okay, now you fix Fv for all V different from V0. Okay, so I've already fixed my function everywhere except at V0, where I still maintain freedom in picking this function. So let me take, so at V0, I'm going to let f V0 be the characteristic function of some, this is some K, or is some open relatively compact, let me just say compact subset, okay, subgroup. Okay. Okay, so I'm going to take my function of this one. I already fixed it everywhere else, and yeah, okay. Maybe I assume that f. I always assume it's not 0 and 1. Okay. Okay. So and at V0, I'm going to take my function to be just a characteristic function of some neighborhood. Maybe just say neighborhood of the identity element, right? I'll just take a characteristic function. Okay. Now, then I'm going to try to string this neighborhood to a smaller and smaller one. Okay. Okay. So okay. So here's a simple lemma. Okay. When this KV0 is sufficiently small, HK intersect support of F is just an identity element. Hence, when this holds, PF of 1 is not 0. So because if you want to understand PF of 1, right, you take H to be 1, so you're just summing over F of gamma, right? And as before, you just have to sum over things in this set, which we know is finite. But you see, this finite set, okay, let's say it has 3 elements. Okay? The support of F is, you know, if you pick F to be like that, right? The support of F, it will be of the following form. I mean, it will be K V0 cross, you know, some compact at other places. Okay. So, you see, suppose you just randomly start with some KV0, okay? You already know you're working with this intersection is a finite set, okay? Now, if you just string this component smaller, you can successively rule out you know, all the elements except the identity in the end, because identity will always be in here. I think if you want to just be more concrete, okay, imagine your group is GL2, okay, your group H is GL2. You have some finitely many matrices with rational entries. Okay, entries are rational numbers, and you pick a place V0, which is a prime number. Okay, and now I'm going to take a certain neighborhood of identity, right, in GL2 of QP. Okay? So I would say, you know, it's worth mentioning that. So for example, you take K of P to be all those matrices gamma in GL and GL2, let's say. QP such that gamma is congruent to identity plus, I don't know, P to the some n, okay, of a 2 by 2 matrix, something like that. Modulo n, okay. Maybe all the entries. No, I don't want to. Okay, so put M2 PP. Okay. Now, as capital N gets bigger, of course, this becomes a smaller and smaller neighborhood. Okay? Now, if you have finitely many matrices, say 10 of them, in GL2Q, this is identity. These ones are not. Okay, all these others are not. That means that there's some entry which is different from, for every of these gamma, there's some entry which is different from the entries of the identity matrix. Okay? So you can pick n big enough to distinguish them, okay, one at a time. Okay? So you can do. Okay, so that's. Okay, so this is one way you can show that the Poincare series, so you can create sort of non-vanishing Poincare series. It's sort of, you can pick your function. In other words, you can fix and pick your function fv, your input function, at all places v except 1. Okay? And so you can control what you want to, because you produce an output, but you would like to have some control over what you got. Besides that, it's non-zero, right? So sometimes you may be forced to pick certain fv. Okay? So you have no choice, in fact. Okay? But as long as you still have 1 degree of freedom, which is at one place you can choose anything you want. Okay? You can sacrifice this one place, then you can ensure that what you construct is non-zero. And this is often, very often done in practice. When one works over a number field like Q, one wants to construct some Poincare series, and one wants to know, and in fact, what one usually do is we take V0 to be the Archimedean place, the place that we are going to sacrifice, and we are allowed to specify what function we take at all finite primes, V, and then at Archimedean place we string this, we take a bump function and string the support. Okay, and then we can produce something not zero. Okay, and because we have good, since we can pick what the functions we are at finite primes, we sort of know what we get at finite primes, but we will lose control of what we get at Archimedean prime. Okay, I want to discuss a separate question, the question of cuspidality. Okay? Right? Because so far the discussion is about showing non-vanishing. Okay? Now, how do you show that this guy is cuspidal? Okay, I guess it's not immediately clear. No good reason. Okay, why it should be cuspidal. Okay, but I just so the point is, what condition can you put on your input function to ensure that the output PF is cuspidal? Okay, so here is one way. Okay, one way which is just a local condition, if you wish. okay, so in the approach to number theory, using adels and edels, okay, the key point of doing that is to elucidate the local global passage, right? So that that many results that one proves in number theory over global fields have analogs over local fields, and in fact, you should understand these analogs over local fields first, right? Before you try to piece together the result to get something over global field. Okay, so here we introduce the notion of cups forms. Okay, that's a concept over global fields, right? And we ask, is there an analog of this concept over local fields? So there is. So here's a definition. Okay. So you suppose you let pi be a let's just say representation of okay, so now we're working over a local field. Okay, then we're going to say that pi is supercuspidal if, see, I don't know, you know, maybe it's better to just call it cuspidal by analogy with the global case, okay, but anyhow, if it satisfies the analogous condition, so what is the analogous condition for all parabolics p equals to mn of h defined over kv, and okay, this is not equal. Okay. So I want to say that the constant term of this representation along n is 0. Okay? So what is the constant term? The space v pi. So v pi is the vector space underlying the representation. Okay? Modulo the subspace sorry, for the v, let's call it w, is equal to 0. Okay, I'm going to call this, I'm declaring this pi sub n. Let me make a few comments about this notion of supercuspidality. Okay, so one can show, and this is it's not trivial, but the following are equivalent. So the following are equivalent. Pi is supercuspidal. I'm going to write SC for supercuspidal because it's a rather long word. Two, pi is not a subquotient of any. Actually, let me assume pi is irreducible. Of any representation of the form okay. In other words, pi is cannot be obtained by a so-called parabolic induction. Statement, except that subquotient is replaced by submodule, and then the last one is the matrix coefficients of pi are compactly supported functions. On H. Let me just say on HKV That's because you have irreducible representation, so anything in the center will act by some central character. So you will not be compactly supported in the z direction, so to say. Okay, let me maybe say what this is. So if we let pi check, okay, denote the dual representation. The smooth dual. Okay. In other words, it's realized on the space of linear functionals. Okay, but I take the smooth part, whatever that means. Okay. Then you have a map from pi tensor pi check to basically just functions on HKV. Okay, if you give me a vector here, a vector there, I'm supposed to write down a function on H, right? And what is this function? Okay, you give me an element H in your group. It's going to take it to, let's say, pi H. Okay. What is this angle bracket? This angle bracket is the canonical pairing between pi and its dual. Okay, this pi check is just a dual space of pi, right? So you have a canonical pairing between a vector space and its dual. Okay. So this is a matrix. A function of this type is called a matrix coefficient. And so you have a map, and this map is actually a H cross H equivariant. Okay, so in general, when you just take two representations, you can always construct such functions, and they will be smooth functions on HKV, but they will not necessarily be compactly supported. But if they are compactly supported, then this is equivalent, according to this statement, to pi being a supercuspidal. Okay, so as I said, this notion of supercuspidality is just a local analog of a notion of cusp forms. Okay? And from a representation theory point of view, one would think that the supercuspidal representations are somehow the most fundamental parts of among all irreducible representations. Why? Because you see, this is because of the statement 2 or 3 that says that to say that pi is supercuspidal is to say that it cannot be obtained by induction from a smaller group. So you would think that those representations that could be built out from induction from smaller groups are less fundamental, or in some sense they could be understood, okay, because you have a very explicit means of constructing them. So the supercuspidal are those which cannot be handled through this type of parabolic induction. So in that sense, you think of them as the most fundamental part among the irreducible representations. But so just like the global case, you should ask the question, do they exist? Because this is just a definition of a property of a representation. So it's not a priori clear that they exist. Okay, one should ask a question. Irreducible representations. Well, okay, if V were an Archimedean place, in other words, KV is real number or complex number, then they don't exist. Okay? Every representation is of this type, so to speak. But when you have a non-Archimedean place, so the answer is that they do. But it's not obviously, but they don't obviously do. Okay, but it's not but so I say maybe I can say no easy construction. Okay, but I'm going to yeah, but as far as I know, there are no easy construction. But I will show you one way of constructing. Okay, so one way, maybe one of the simplest way. One way is maybe via reduction mod V. And let me just illustrate, okay, by example. Suppose your group is GL2. Okay. Let me just work over QP, let's say. Okay. Then, I mean, this contains. So I'm looking at GL2 EP. Okay, and this contains a K GL2 ZP, which is actually a maximal compact subgroup. Well, these are 2 by 2 matrices whose entries are in ZP, so you can do reduction mod P. You are going to get a finite group of V type. This is a finite group of V type. Okay, now you see the notion of supercuspidality makes sense for such a group as well. Okay, you will simply use the same definition. Okay, where instead of KV, you just pretend KV is a finite field. Okay, you look at representations and you can define the notion of supercuspidal. Okay, representations of this finite group of V type. So, suppose you take tau a supercuspidal representation of GL2 FP. Now, you can pull it back to this group. Okay. Then you get a representation of this, because this will be a finite dimensional representation. Okay. And then you can set pi to be a reduction. Well, I see now. I should let me. I don't want to deal with the center, so I look at PGL instead. Yeah, so this is K of tau. Okay, so I have tau. I can always pull back to K. Then I induce, and this thing is irreducible. Supercuspidal. I mean, this thing is irreducible. So that's what I mean by reduction mod V construction. Okay? But you see, this is the ingredient of this construction is a supercuspidal of this finite group. So you should rightly ask, do these exist? Okay. And of course, for GL2, you can check by hand that such things exist. Okay. But in general, I mean, for general, let's say for general H, this exists by the work of the Lin and Lustig, who give some very general constructions of representations of this type of finite groups related to Lie theory. So that's what I mean by there somehow is no easy construction, because even in this construction, you ultimately rely on knowing the existence of supercuspidal representations, sort of, for these finite groups. And of course, this construction nobody says is exhaustive. I mean, so a supercuspidal representation that comes from this way, it's called somehow a depth zero. Okay, so these representations are of depth zero. Depth is like it's analogous to the notion of conductor. If you have a character, like say a Dirichlet character or something, there's a notion of conductor, which give a measure of the biggest neighborhood on which the character is trivial, right? So for a possibly not one-dimensional representation, the notion of conductor is this depth. So the point is to suggest that this depth 0 supercuspidal, they are somehow the least ramified supercuspidal representations. Maybe let me take 5 minutes to just complete something, then we can take a short break. Okay. All right. So, okay. So I come back to the question of how do we construct cusp forms, right? So, suppose you have supercuspidal representations at hand, then here is how you can ensure that you construct a cusp forms. Okay. So what you do is okay, so you fix V naught, right? Place, and let pi V naught be a supercuspidal irreducible representation of H K V naught. Okay, and now you're going to take your ingredients in the Poincare series. Okay, let this be a matrix coefficient of pi V naught. Okay, then this is compactly supported, right? So because as I mentioned over there, one of the equivalent conditions is that this thing is compactly supported. Now let me now assume the H is semi-simple, so that that Z is trivial, okay? Because I don't want to. Otherwise, I have to add this compactly supported modulo Z. So I have this. So this is a valid ingredient I can use in my Poincare series. Okay. Then the claim is that this PF will be a cuspidal function. Okay? If your input is a matrix coefficient of a supercuspidal, your output from the Poincare series construction will be a cusp form. Why is that? Well, why? Okay, so because you see we have to compute all constant term, right? So for any parabolic, we can consider. I'm going to consider. So consider just I'm going to consider the linear functional. So let me call it L.N. Okay. Define as follows. So if you give me some, let me say some element y in here. Okay. Of course, I will simply take it to maybe like tensor. Okay. V different from V naught, F V. Okay. I already fixed the function at other places. All right. So I have this function. I can look at the associated Poincare series. Okay. I'm going to write this upper V naught to mean this tensor here. Okay, and then I will compute its constant term. Okay, so I get a number. So this means that basically I'm fixing my function. Again, I'm fixing all the components outside of V naught. And at V naught, I'm just letting it vary. No, okay, that's not what I want to say. I want to put F sub V, F sub phi here. So what is F sub phi? So F sub phi is a matrix coefficient. So it will look something like that. I mean, I fix this. Okay. I let phi vary, then I get all kinds of functions. So this is a linear form, and it's very easy to check that it is n invariant. Okay, so L n factors through this projection. We factor through this projection. Okay? So this is because, I mean, recall, right? This is this thing modulo or such things. So all I'm claiming is that if you take vectors of this form, they will be in the kernel of this map. So it factors through this quotient. Now, but since pi is supercuspidal, pi n is 0, right? That's the defining property of supercuspidal. Okay, so Ln is identical to 0. Okay? So this is saying that when you form a Poincare series, whereby at some place V0 you are taking the matrix coefficient of a supercuspidal representation, then the Poincare series you get is will automatically be a cups form. All right, so just so to summarize what we have done in this first hour, if you want to produce non-zero cups forms, here is what you can do. Okay? So fix two places, V0 and V1 of your global field K. Okay? At V0, you let F V0 be the matrix coefficient of a supercuspidal representation. Okay? At V1, you let F V1 be the characteristic function of some open compact neighborhood with K V1 sufficiently small. I mean, meaning I'm allowed to make it as small as I wish. Okay? And at all other places, just fix any FV. It's up to your choice. You have total freedom in choosing this. Then okay, so then for all sufficiently small KV1 PF, okay, so F is just the tensor product or product of all these is non-zero cuspidal. Okay, so maybe we take a 5-minute break. Yeah, 5 minutes. I brought some cookies from Singapore, so I thought I'd share with all of you. Let me see if I can open this in 5 minutes. Oh, it's not so hard. Okay, this is some pineapple cookies. So I just pass it around. Yes, that's okay. Yeah. Just now, so let me formulate the main theorem that I will talk about. Okay, in this. Okay, so we are. So suppose we are given the following data. So K. Global function field. Okay, so as I mentioned just now, probably what I say it will go over a number field too. It's just let's just focus on one instead of having to. Because the main purpose or application of this theorem that I'm going to state is in the function field case. Okay, but I will make these comments later on. Let me just formulate the theorem first. So with L and let S naught be a non-empty finite set of places. Okay. Let H be a connected reductive group. Over K. So as before, Z will denote the identity component of its center. Let me let N in H be a smooth connected and split, a K-split unipotent subgroup of H. I will make some comments later on some of this data. But it takes a long time to write down even the statement, just because all the ingredients. So chi is an automorphic character of NA. So of course, this is not a group. Okay, so let me just say it's an automorphic unitary character of NA. It's a character of NA that is trivial on the rational points Nk. Given omega, so this is basically a central character. And for all places in this finite set S naught of places, pi V naught is an irreducible supercuspidal representation of H of K V naught. Okay. So I'm given this data such that so there's a condition that ties in the things above. So certainly I want this pi V naught to have central character to be equal to the given omega V naught. But I also want this the space of n equivariant map from pi V naught to chi V naught to be non-zero. Okay, so this type of condition is usually called, we usually say that pi, so we say pi V naught has, so I'm just combining these two conditions together. So it has central character, omega V naught. Well, okay, this Z is not exactly the center. It's just the identity component. So, but I will nonetheless call it the central character. Okay. I don't want to call it a connected central character. So, okay, and so that's what the mean, and pi V naught is n K V naught, pi V naught distinguished. So this distinguished condition just means that this Hom, the space of n equivariant Hom from this guy to chi is not zero. Okay. Now, of course, in this, so this is the given data. So in this data, of course, n could be a trivial group. Okay, if n is trivial, then of course chi is nothing. It's just a trivial character. Then there will be no conditions here. Simply saying, the condition simply says that the central character of pi V naught is this omega. Now, also notice that in this data, right, basically everything is global, right? All these groups, everything is only global. The only local things are this. Okay? And then, what is the theorem?
Excuse me, do you assume characters are unitary?
This one. You mean this? Yeah. So this one, yeah, sure. Maybe I should. Yeah. So let's assume it is unitary.
And the other one.
The other one, I think, it's automatic. Yeah, it's automatic because this quotient is compact. So I have this data, and then the conclusion is that there exists cuspidal representation pi. So any cuspidal representation is a tensor product like that, okay? Such that, okay, so there are three conditions. Firstly, for all V naught in S V naught, oh, maybe I want to call this a capital pi. Okay, the pi v, the V naught component is the given ones. Okay. So let's say for all V naught not in S naught, sorry, for all V, pi V is is a constituent, or is okay, let me say it's a submodule of an induced representation okay, where with PV a minimal parabolic over KB. So for example, suppose your group H was split, then this PV will just be the Borel subgroup. And pi V, when you restrict this representation to the derived group, it has depth 0. Okay? So I mentioned just now at the end that this notion of depth is like the conductor of a character. Okay? So depth 0 means the ramification is very small, very minimal. Okay? Now, why do I restrict to the derived group? Well, you see, it's because the central character is, oh, you haven't said that yet, but okay, so anyhow, the third condition is pi has a central character omega. I mean, that's part of the given data. You see, this given data at a place V, right? I mean, your central character will be omega V, and that could be highly ramified, right? You have no control. It's part of the given data. So that is why I could not say that pi V itself has depth 0, because if the central character is highly ramified, there's no way it could be depth 0. Okay, but besides that, it's not a problem. Okay. So for example, you may assume H is semi-simple group. Then there's no Z. Z is trivial. There's no omega. Okay, so then and the derived group is just itself. Okay, then we're saying it has depth 0. Okay, so it is, and pi has, I mean, okay, let me just say it's globally distinguished by n chi. Yeah, so I introduced the notion of locally distinguished, meaning there's an equivariant map from pi v naught to chi v naught. What is globally distinguished? Mean, i.e., the integral sum phi. Okay, so I guess the upshot is you have some groups and characters over in the global setting. You have a finite number of supercuspidal in the local setting. Then you can globalize them to a cusp form so that the global analog of those local conditions continue to hold. Okay? Now note that this map, so note, the map from pi to c, taking phi to that integral, is an element of this. But in the global setting, I mean, we are not requiring that this space is not zero, but a certain explicitly constructed element of that space to be non-zero. Okay, that's what globally distinguished. It doesn't mean that we want this space to be not zero, like in the local case, but that specifically constructed integral to be non-zero. Okay, so that's the theorem. So let me just highlight a couple of special cases.
Can I just confirm one
Yes.
statement? So in the first part, is it true that it is an isomorphism or isomorphism map to a right-hand twist?
I think I want isomorphism.
Okay.
Yeah, I want
Correct.
isomorphism. Yeah. Okay, so okay, I will make some comments. I will just talk around this statement, but let me highlight two special cases. So one, of course, is when n is trivial. I mean, that's possible. I mean, I was just going to say that n need not be non-trivial. Okay, but the other case, which will be so in the applications that I will discuss, maybe in the rest of the lectures, these are the two cases that will actually be used. Okay, one is when n is trivial. The other case is when H is a quasi-split. So it has a Borel subgroup. B defined over K. Okay, and N is the unipotent radical. Of B, and chi is what is called a generic character. So this will be another instance of this theorem, but these are the two cases that will be applied. Okay. Okay, so what is the point of this theorem? So you see, the point of the theorem is not about just producing, but just now at the end of the first hour, right, I end with a summary that says that if you are willing to take a matrix coefficient of a supercuspidal, okay, and at one place you are willing to string the support of your test function, then you can produce non-zero cusp form by Poincare series. Okay? But you see, we are not interested just in producing elements in this space of automorphic forms. We want to understand the irreducible summands of it as a representation of HA. Okay, so, but once you have a non-zero vector, you can of course look at the HA submodule generated by that vector. Okay? Now, if you have a cusp form, okay, it is in L2, and I said it is a semi-simple representation, right? So the HA module you generate will be some semi-simple representation. So you will break down into direct sum of irreducibles. Okay? And you can take any one of those. Okay? And it will be some tensor product like up there. Okay? Then of course you would like to know, you would like to say, to ask whether you can say more precisely what the irreducible cuspidal representations you obtain. For example, what can you say about this pi v? Now, so the purpose of this theorem is to say that you have very good control of what the pi v is for every v. Okay? Because so at this point I said S0, you have some data. right? That you're trying to globalize. So of course, you would like to say that the local data is just what is given. Okay? But at all other places, I mean, you cannot actually say what it is, but you can say that it is induced from a minimal parabolic. So for example, a Borel, if H is quasi-split. And moreover, the ramification is very little, okay, because it's depth 0. Okay, so in proving this theorem, you see, it is not possible to, okay, just to say that how to construct this thing is going to be by Poincare series. Okay, however, to show that Poincare series you construct is not 0, you see, you will not be able to use this shrinking the support of the test function at one place, which was the argument used at the end of the first hour. Okay? Why? Because when you take a function whose support is smaller and smaller, so basically approaching direct delta function, right? Then, so you know very well where it's located in space, because it's some very small neighborhood of the identity. But then, if you take this type of test function, you basically lose total control on what the v component of pi v of pi is. Okay, suppose you sacrifice a place v1. This is where you string the support of the test function. Then you will not be able to say anything about pi v1. Why is that? This is basically a manifestation of the uncertainty principle, right? When you take a function, say on the rail line, you let it approach direct delta. Then when you take Fourier transform is you're looking at the spectral expansion of this function. Then the Fourier transform of direct delta is the constant function, 1, right? So if you take a function which is very localized in space, then on the spectral side, it is very spread out. You have, in other words, you don't know what you get. Okay, so in proving this theorem, it is, you see, you don't want to show non-vanishing by shrinking support at one place, because that will cause you total loss of control of what representation you get at that place that you are shrinking the support. Okay. Anyhow, I won't discuss the proof today. I'll discuss the proof next time. Let me make another comment. Okay, another comment is the following. So here, when I talk about a unipotent group, I have decorated it with a number of adjectives. Okay? Now, if you are used to working in characteristic 0, local fields or global number fields, then maybe all those adjectives are not necessary, because any unipotent group is automatically spool connected K-split. Okay? Actually, let me define what I mean by K-split. Okay, so let's erase this, because it's not part of the theorem. So make a remark.
So chi shouldn't be trivial.
Sorry?
If chi is trivial, so the last condition may contradict cuspidality. So chi shouldn't be trivial.
Yes, but if no, I mean this n need not be unipotent radical of parabolic.
Just to clarify.
Yeah, I mean no, chi could be trivial.
Of course.
Yeah, chi could be trivial. Yes.
If n is so unipotent radical of some parabolic subgroup, chi shouldn't be.
Yes, because, but then this condition would not be satisfied, right?
Oh, thank you.
Yeah, so it can be. You don't have to insist it there, because it will be ruled out here. So let me say, what is K-split? A unipotent group, say U over if K is K-split if it is a successive extension of the additive group GA, over K. Characteristic 0. In fact, as long as if K is perfect, for example, if characteristic of K is 0, any unipotent group is K. But if it is not perfect, say there are weird unipotent groups. And in this theorem, I don't want to consider this weird unipotent group. Okay, so since I myself only come across these weird unipotent groups recently, I thought I just take some time to share them with you. Okay, so I'm working with a smooth connected unipotent group. Okay? I'm assuming smooth and connected. Okay, so here's an example.
Excuse me, do you have a similar results over number fields? Or
Yeah, so yes. So this theorem that I state would hold, I think, literally over number field as well. Okay, yes, it will hold literally over number fields. Okay, and in fact, for number fields, you can prove this by using this stringing support argument at the Archimedean place. Okay, why? Because as I said earlier, when you string the support, so pretty much in this stringing support, right, you can choose your test function or other place. So you can somehow arrange, at the other places so that the output will be what you want. Okay, but at this place that you string the support, you lose total control. Okay, but if that place is an Archimedean place, so what if you lose total control? Because even though you don't know what pi v0 is, but if v0 is Archimedean, then it is known by Harishchandra or Kasserman that every irreducible representation is contained in an induced from minimal parabolic. Right? So because of this theorem is, in the function field case, is more delicate because you don't have this Archimedean place for you to do this stringing support argument. Yeah, okay, thank you. I should make this remark. So it is true over number field, and it can be proved by this stringing support. And this is usually how it is proved, actually. Yeah. But the challenge in the function field case is that you do not have any place where you can sacrifice, because every place is like a p-adic place in some sense. Okay. Let me do an example of Rosen-Lake just to illustrate what this guy is. Okay, so of course we are working with and of course for the function field, like a field like will be the type of field we are looking at. So this type of field, this type of field are not perfect. Okay, they are purely inseparable extensions. And that's why I had to put all those adjectives in there. Yeah, I should say that also the other remark I want to make is that if a unipotent group is k-split, then as a variety, it is just isomorphic to affine space of some dimension. All right, so let's see. Let's let K be a non-perfect. For example, this field, function field, your rational functions in one variable over finite field. Let's take okay, so let's take A. Suppose you have something which is not a p power. Okay? And let's consider the following closed-up scheme of Fi2 space. Of course, this is a unipotent group, commutative unipotent group, just a vector space of dimension 2. Okay? I'm taking this something defined by this equation. So all pair xy that satisfy this equation. Okay, so note that this is a K subgroup of GA square. Why? Because if you take 2 points on this curve and you add them, this equation still holds. This is because of the x1 plus x2p is x1p plus x2p in characteristic p. I mean, non-perfect field, sorry, of characteristic p. The same p here. Now, okay, so So you have a one-dimensional algebraic group, if you wish. Okay. Now, what is this one-dimensional algebraic group? Now, over this view, okay, so this is a purely inseparable extension of K, okay? Claim is that U is isomorphic to GA over here, okay? How? So this is Y, okay, so Y. Well, because if you're working over this view, let me call this element B. So B is a pth root of A, okay? Then the equation, yp equals to x minus A xp is bp xp, right? So this implies that if you bring this to the other side and using this miraculous binomial theorem, the equation is rewritten like that. Okay? So you are going to define an isomorphism by sending xy to, I guess, y plus bx. Okay. I mean, so firstly, you can change your variable on the affine2 plane. Instead of using xy, you can use x and y plus bx. Right? I mean, this is a vertical transformation, okay, of your vector space. Okay, then we are saying, okay, you just take one of these coordinates. Then this equation allows you to work out the other coordinate. Okay. So, and this is a group. This is a group isomorphism. Okay, because with this addition, it's clear. It's a linear map. Okay, so so this group is a unipotent group because over algebraic closure, it is just GA. Okay, but over K, U is not even isomorphic to GA as a scheme. Okay? And I'm not going to write out the proof, but the way usually is proved is that, well, U is a curve, right? It's an affine curve, but it has a canonical, there's a canonical smooth projective curve associated to it. It is canonical completion or compactification. So if you work out what that is, okay, for example, you can just, if I'm not wrong, you can just take closure of this in P2 or something like that. And then you find that this smooth projective curve, which completes this U, it just needs one extra point at infinity. And when you compute what the residue field at that point at infinity is, you get this field. Okay. So then you see that you have a point which is not K rational. I mean, it's not defined over K, but defined over this purely inseparable extension, whereas GA would not have such a thing. I mean, if your curve were GA, then its compactification is P1, right? The extra point is P1, at the point at infinity, the residue field is still K. In other words, the point at infinity is a K rational point. Whereas for this U, if you compute what is the regular model is, there's also one extra point at infinity, but that point is not K rational, but it's KB rational. So that shows that as schemes, they are not rational. Okay, so here is an example of a weird unipotent group, okay? And as you can see, it was discovered by Rosenlich, so it's a long time ago, probably half a century ago, okay? And following Rosenlich's work, Tietz did a systematic study of the structural theory of unipotent groups over arbitrary field. Of course, only non-perfect ones are the interesting ones, okay? And if you, unfortunately, he never wrote down anything, so, but there are two references, good references for this. So one was the paper of Osterley, Inventiones 78, 1984, in this paper, what he did was he computes the Tamagawa numbers of unipotent groups. Now, if you think in terms of like number fields, you think this is a trivial problem. Tamagawa, unipotent groups have Tamagawa number 1, okay, or something like that, okay. And this is the case. So the interest of this paper is he computes it for even function fields, which are non-perfect, where there are lots of these weird things, okay? So first, he needs a structure theory that tells you what are all these weird things. Okay? This was supplied by Teets, which he wrote up. And chapter 5. And then for each of those, he computes the Tamagawa number, and yeah, okay. I'll let you check out, see what the results are. They're quite interesting, though. Okay, the other good reference, fairly recent, is the book of Conrad, Garber, and Gopal Prasad. This is their book, Pseudo-Reductive Groups. And in Appendix B, they discuss this structure theory for unipotent groups over non-perfect fields. Yeah, so this so-called, these weird groups, they actually have the name. I mean, so Teets call them, I'll say it in a moment. Call this group K. So the definition was U over K is now if there is no map. Schemes from trivial to U except constant map. So somehow in non-perfect view, a unipotent group is going to be built out of the split ones, the K-split ones, and these other ones. Okay? Now, the way you should think about this is analog of the notion of anisotropic torus. Okay. Because you see, when you look at torus, you have a notion of split torus. Split torus means it's a successive extension of GM, right? So if you, anisotropic torus is if there's no morphism of groups from GM to T, right? It doesn't, except for constant map, right? Then, except for the trivial map. Okay? There are no group homomorphisms from GM to T. You could, of course, adopt the same definition here. That you could say that there's no group homomorphism from here to there. But in practice, they adopt a stronger one. Okay, that's better, easier to develop the theory to adopt this definition. Okay, now, so from this point of view, it looks like analog anisotropic torus. And in fact, from another point of view, so if K is a local field, the local function field, and U is a K-wow. No, then U is K-wow, if and only if UK is compact. Okay, so this is another sense in which it is also the analog of anisotropic torus, because for torus, the anisotropic torus over local field are precisely the ones such that TK is compact. Here's another, so let me give another example. Because again, I was kind of shocked to realize this example, but it has been known for a long time. And it's again in the same setting, so you let L be K. So in setting as over here. And now let's let G be the restriction of scalars of GM. Now, normally, if we take a separable extension and we do this restriction of scalars, we say this is a torus, right? It's a torus. Note that this contains GM as canonically. Right? Because the point is that for any extension field R, any K algebra, the point of this is K tensor L contains R cross GN. Now let's let H be G mod GM. When you take points, well, because so for example, when you take points over K, you see that I mean, it's basically this, right? Okay. But you see, this is in this group all elements have order P. I mean, P or 1, I guess. Okay. So all non-trivial elements have order P. Because when you take a rational function in the variable B with coefficients in K, when you raise that to the P power, you are going to get a rational function with over the variable A. So anything in L cross, when you raise to P power, it lands in K cross. And so all these elements will be unipotent. So in fact, this group, H, is isomorphic to GA P minus 1 over L. So in other words, this restriction of scalar is not a reductive group. I mean, it has a torus, a reductive part, and all the other parts are unipotent. But then again, it's not a split. This will not be a split unipotent group. Okay. Over L, it is split, but over K, it is in fact K1. Okay, so I think this is, if that's not weird enough, this one is, I hope this is weird enough. So one has to be a bit careful when one works with unipotent groups. So in the theorem, I don't want to consider these groups. Now, but let me know that for if your unipotent group is the unipotent radical of a parabolic, then it will be K-split. Maybe I will close by formulating a corollary of the theorem. Okay? So the use of the theorem is the following. So suppose you want to prove a certain result in representation theory of a local group. Then, so there's a certain statement P that you want to prove for any irreducible representations of a group over a local field. Now, very often, you can, if your representation pi is not supercuspidal, so it's contained in some induced, parabolically induced representations, then very often you can reduce that statement P to some analogous statement of the inducing data, which is on a smaller reductive group. So by induction on dimension, you may assume that that is already known. Okay? So then you are left with supercuspidal representation. Then one very standard technique for, proving some statement or property about supercuspidal is to globalize, okay, and prove a certain result in a global setting, and which would imply the desired statement at a local local setting. Okay, so when you do this argument, you globalize. Okay, so you prove some global statement, but then in order to inherit that local statement that you want, you usually need to know that at all other places, V, you already know that pi V satisfy this statement P. Okay, it's only then you could extract this property, V naught. And that is why in this theorem, we want to have control over all the pi V and all other V's. Okay? Now, but if that is the main application, so in other words, the main application of this globalization result is to prove certain local property or local statement, then very often what you start with are simply some local data. You have some group over a local field, you have some supercuspidal representation, maybe with some properties like n-chi distinguished, but everything is over local field. There's no global field at all. Okay? So in order to apply this theorem, you have to put yourself in the setting, right? In other words, you have to equip yourself with all this data first. Now, if you look at this data, everything is global here. You need a global field, you need reductive group over K, you need this N. So, maybe, okay, so that's why I wanted to say a corollary. In this corollary, you are only given totally local data. Okay? And corollary, so F local field, let's say characteristic P 0. So you are given, so these are the groups over F. Okay, so you have some parabolic. Okay, you are given this. So these are groups over local field. You are given some, omega F. You are given this chi F. I will confuse this group with their F rational points. Some characters before. Okay, but okay, then, but I want to put a condition such that chi V lies, the MF orbit of chi F is open. Maybe I will make a comment about that. So, and suppose you are given pi 1 to pi A supercuspidal representations of HF with central character omega F. And which are NF, chi F distinguished. We're given this data purely locally. So then the conclusion is there exists the following global field K with A places such that KDI is isomorphic to F. So basically, you have to globalize all of this. So you will have the analogous picture over K, globalizing. Maybe I call this 1, 2, 3, 4. Globalizing 1. Globalizing 1 at each pi. Okay, I will have this omega. Globalizing 2, I will have chi such that chi bi and chi f are in the same MF orbit. You see, you can't really globalize chi m necessarily, because, for example, if you give me just a local character of over local field QP, I mean, there's no reason why it could be a local component of a global character of A mod Q. No, this is about the best you could go. And okay, so this corollary is, you know, is a corollary of the theorem. So, but the difference is that you are only given local data. So in order to apply the theorem, you must globalize all these guys, right? So suppose you come to this stage already, meaning you have globalized all these things, then you can apply the theorem. And then the theorem will tell you that, down here, that there will be a cuspidal representation pi, as in theorem. Meaning you will globalize the pi i's, it will be a central character omega, it will be globally n chi distinguished. And at places different from those given ones, V1 to VA, it will be in a principal series induced from minimal parabolic and has depth 0 and restricted to derived group. Okay, I think I'll stop here.
So, any questions or comments?
Next time I will discuss the proof of the theorem and the corollary.